Hello. Hey everybody and welcome to my live stream. Welcome to my YouTube channel. It's November the 19th in some year. Yeah, I guess it's time again to do some live streaming, which I will be doing today. I don't know. I guess let's get started. Not that one. Not that one. Thanks, OBS. Let's do this one. Yep. Okay. Hello, everybody, and welcome to my cool stuff live stream where I only stream stuff that I think is cool. I think we're gonna do some more TenderJIT hacking today. Just I don't know, because that's what I feel like. Yeah. Oh yeah. Just please make sure to like and subscribe. Smash that one of the buttons. All right, we're gonna do some TenderJIT hacking today. As always, if you have questions, like put them in or hi Penelope. What's up, memers and dreamers? Oh boy. Welcome to the live stream. Okay, let's do some stuff. Happy Friday, everybody. Woo! Happy Friday. I need to test though. Is this okay? No. There's I was trying to tell if my green screen is broken or if there's just junk on my screen, and it is just junk on my screen. All right. Happy Friday, everybody. Woo! We made it. Last week was RubyConf, and it was really, really fun. It was super fun to see people in person again. I really enjoyed that. I think I gave a talk at RubyConf. I don't know if it's online yet. If it is, go see that. Penelope asks, did you enjoy eating a burrito with me? And indeed, I did enjoy eating a burrito with you, Penelope. And for those who haven't seen it, you should check out her Twitter for a photo of that, which is very amusing. I want to say thank you all for coming here today to my live stream. This week has been not super fun, so I'm happy to do some streaming and work on fun stuff today. So also please put good jokes in the chat. I like good jokes. Okay. So we're going to talk about TenderJIT a little bit today. I think I've mentioned this in previous live streams, but TenderJIT doesn't support auto compilation. So if you like it won't compile stuff for you. That is a limitation right now. And we can do it, or I can do it. Actually, if we have time today, I've got a branch where I've got that started and we can take a look at it. But right now it doesn't do it. So you have to do manual compilation like this. So you say like, I'm going to use my little fancy drawing thing here. Let's see. Got an arrow. So you have to manually say like, does that show up there? No, it doesn't. Okay, that sucks. Never mind then. You have to say compile some particular method. So you tell it, hey, compile this method, and then like enable the JIT and then call the method. So in the future, we'll not have to do that, and maybe we'll look at it today, possibly. No, okay, come back here. There we go. But it is an opportunistic compiler. I was trying to figure out a good name for this. I think opportunistic is pretty good. What I mean by that is like if you say, so for example, here we like compile foo, and then foo calls bar. So when we enter that JITted method, the JITted foo method, it'll say like, hey, I'm going to compile, like, it's like, oh, I got to call bar now, and it looks up bar, and it's like, oh, bar hasn't been compiled yet, so I'm gonna go ahead and compile it. So it'll compile things that it calls, so it'll compile callees. But I want to talk about stuff that we can't compile right now, because like that's where we gotta improve, right? One thing is like it can't. So TenderJIT can't see through C. Get a C. So in this case, like I wish I could draw on this screen. Killing me, Keynote. So we can't like, all right, so foo calls into some C function, and then you'll see here the C function, it calls back out to the LOL function, and LOL function will do stuff. And the problem is like the JIT compiler can't look at the C code and tell that the C code is actually calling back out to Ruby code. So that's kind of a problem here. It's a little limitation. And I mean, YJIT can't do this either. Yeah, interpretive. Oh yeah, I could totally do that right here. Yes, thank you. Green screen. Green screen limitation. So Penelope asks, could we add instrumentation to RB fun call to do that? And we could, but we don't actually have to. When you do an RB fun call, it'll actually go back through the virtual machine. So it calls back into Ruby's VM, and Ruby's VM is like, oh, hey, I gotta call this, like I gotta execute this function now. And a couple weeks ago, we were looking at that code, and Ruby's VM will say like, oh, I got to execute a Ruby function, and that's an opportunity for the JIT compiler to execute. So like in this case, if we were using a JIT compiler that had automatic compilation, then the LOL method would get automatically compiled if we called it enough times. So for example, in this case, like YJIT would compile LOL because it has automatic compilation. So it would do that. But we don't have that in TenderJIT right now. So we have to manually compile it. So in order to work around this, we have to say like, okay, we're going to compile foo, and then we're going to compile LOL. And since the interpreter, since the VM will like check on the method call to LOL, it'll see, oh, there's actually a JIT compiled version of LOL, so I'm going to call into that thing there. So we have to specifically say like, hey, compile this, compile that with TenderJIT right now, which hopefully we will fix soon. Another issue is like we can't like in the case of unsupported instructions. So let's say for example we have this code where we have a not in, like we're doing a not. And let's say the JIT doesn't support not. So what happens is like the JIT compiler will go through and it'll try to compile this method, and it hits the not instruction, and it's like, I'm not gonna compile this. I'm not gonna compile this because I don't know how to compile it. So if that happens, then anything after that, it won't compile those instructions. So in that case, we have to exit the JIT. So we'll say like everything before that instruction can get compiled and executed, but that instruction and anything after it will not get compiled and executed. Another problem with this is that this type of unsupported instruction, it impacts callers as well. So let's say we have this example here, calls foo. We have a whole bunch of stuff at the beginning of calls foo that could be that could be like JIT compiled, or it is JIT compiled. Let's say all of calls foo is JIT compiled. So we do a bunch of stuff at the beginning, then we call foo, and then we do a bunch of stuff afterwards. And let's say the JIT compiler supports everything in this function, so that we're great. But the problem is it's calling into foo, and we don't support the not instruction right now. So what will happen is the JIT compiler will call into foo, and it'll execute as much of foo as it can. And as soon as it hits an instruction that it can't execute, it exits all the way back up to the very top caller. So imagine wherever the JIT enters, like that's where we go back. It winds all the way back up there and exits. So in this case, even though we were able to compile all of calls foo, everything after the call to foo won't get executed inside of the JIT. Johnny Lee Rollins asks, one of my favorite parts of Ruby has been fiddle. Would TenderJIT basically be at odds with fiddle? No, absolutely not. TenderJIT heavily relies on fiddle. Please see my RubyConf talk when it is out. Okay, so like, what do we do here? Basically, the solution is to just support more instructions. So we have to try to maximize the amount of time that we're inside of the JIT. We want to do our best to eliminate all exits. And I was gonna demonstrate op not today, so I was like, "Oh, let's do op not." It's I wrote these examples, but then I got a PR here that implemented op not. So op not is the instruction for this for the not thing. So I have to find another thing. I thought it was very funny. I'm like, "Oh man, this is the thing I was gonna do in the live stream." But it's implemented now. So, what I've been doing for figuring out these different... Oh, my video's up. Thank you, Penelope. My video is up, and you know what? I'm going to put that in the show notes. I'll put a link to that in the show notes. So what I've been doing is I've been looking at opt-caret, so running opt-caret, and then checking, like, okay, what instructions are not supported yet, and then go and just implement those instructions. So we're gonna do that. We're gonna do that today. Let's switch over here, and no more Keynote. Thank you, Keynote. But first, I want to show you this is the opt-caret benchmark, and I had to modify it a little bit because of the issues that I told you earlier. Since we can't see through C functions right now, and we don't have automatic compilation support, I have to specifically say, hey, I want the run method to be compiled. And if we go read through the run method, there's some stuff in the run method, like it calls into a C function, that C function calls into the step method, or maybe there's an exit. I can't remember exactly what the issue is, but the step function is really like the big part of opt-caret. So I'm specifically saying here I want to compile these things. And then here we enable the JIT, run the NES emulator. And here, this tells us how many times we exited the JIT compiler. Where did the code font... Okay, love the code font. The code font go... I don't understand. So this code font... The font I'm using here is Inconsolata. The one I used in Keynote was Comic Code. You can go look that up. It is a Comic Sans, a monospace Comic Sans thing. I'll put a link in the show notes. All right, so we can see the number of times we exited here. Actually, let's fix this. Be like exits, so it's more clear when we output it. So this, one of my favorite tricks is if you do like a P and then you do a hash here. So this is a hash, right? We could actually rewrite this as like that, but I'm lazy, so I don't do that. It'll print out a nice little thing there. It just says like give like a label to the thing we're printing out. So this prints out the number of exits. This prints out the number of compiled methods, not the names of the methods, just the number of methods. Let's do executed. So number of executed methods, and then this is like this here prints out the instructions that we exited on. So we can see like, okay, we hit this instruction and we couldn't support that, like we couldn't do that one, so the JIT compiler just quits. So we're going to run this and see how it goes, which I have here. Yeah, let's just run it. And it gives us an exception. And the exception is, okay, I've run into this before. Actually, the exception is kind of good. The exception is that we're compiling a bunch of code, but it fills up our JIT buffer, and our JIT buffer is only 16K, so it can only hold 16K worth of data, and we hit the limits of that. So we're gonna need more machine code here. So let's go fix that. And I think that's in. So this window I'm in TenderJIT. Let's look here. So I think I put we should probably make this configurable. So if anyone wants to send a PR for that, we should make this. You'll only ever need, exactly, yes, you only ever need 16K. That was the idea. So right here, actually this math is kind of funky. It's like 4K, so 4K times 4 times 3, because I wanted to do, we should rewrite it like this. Actually, I'll show you all what this is used for. So we actually split. Where is it? We actually split the memory buffer into 3. So we have one buffer here. What is this one? So this is the actual executable memory. The heck is this? Here is the actual executable memory. So we allocate whatever that is, 16K times 3. And we use, so it's essentially treated as 3 different buffers. Hi, Charles. And we use one of them for deferred calls. So as I said, like in previous streams, just like YJIT, TenderJIT is a lazy compiler. So it'll insert like stubs where it wants to like get runtime values, and it'll execute those stubs, but those stubs only end up executing once. So that we store those inside of a special buffer, like I guess a non-mainline buffer, essentially. Then we have an exit buffer here. So anytime we need to exit back to the interpreter, like this, we write out exits to this thing because we also expect those to be fairly rare, hopefully. And then we have a third buffer, which I guess this is the JIT buffer. So this is the third buffer. This is our mainline code buffer. So this is the one where we we hope we stay in that buffer most of the time. Anyway, that's why it's 3. So we have 16K times 3. So let's just do like 10. Seems fine. We should probably make that configurable. Let's see. So if we run this again, let's see what the output looks like now. It's doing something. That's nice. So we exited, okay, 32 FPS, our checksum. This is the normal output from optcarrot. We've got 181 exits, so we exited back to the interpreter 181 times. We only compiled 7 methods, but we executed those 7 methods 104,000 times, which is kind of that's nice. And our current problem is opt-EQ. So opt-EQ is the one that we're exiting most on. Get constant. So we exited twice on get constant, and I really don't want to explain that. It's very nasty, but trust me that we don't care about this one. We care about this one. So let's implement opt-EQ, and oh no, there. Hey. So like, where is it? We implement that in the IC compiler in here, and for each of the let's go over here to tabby. I'm doing LCD so that this LCD in Vim so that this particular tab is now in my checkout of Ruby. So if I do like pwd here, it's there. But if I go back to this tab and do pwd, oh, it's in TenderJIT now. Okay. So here, let's do e -ns.def. Oh, come on. And we'll go to opt-EQ. Opt-EQ. So this is, I guess, for equals. It's an optimized case for doing like double equals here. And it takes a call data, it takes a receiver, an object, it pops a receiver and an object off of the stack. So it pops 2 things off the stack, and then it pushes another value onto the stack. And interestingly, if we go look at opt-equality, like it does a bunch of stuff. And I don't really want to figure out what that stuff is. It does a bunch of stuff. Like, I guess it does some specialized equality. Oh yeah, look at this. So if we got two numbers, it's like, oh, I'll do comparison on 2 numbers. Symbols, constants. Otherwise, like, blah, 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 whatever. Bunch of different optimizations. However, if any of these fail, like let's say you have an object and you implement double equals on it, it comes back to this thing and essentially just does a method call. So opt-EQ, in our worst case, it basically falls back to a normal method call, which is exactly the same thing that opt-not does. So guess what we're gonna do? So essentially opt-not, the implementation for that is exactly the same as just doing a method call. So we're going to do the same thing for opt-EQ, but I suppose we should write a test for it because I'm a good programmer and do that. Opt-EQ, right? Yeah. Oh, okay. I guess let's implement it. Def, what do we do? You know, do this. I'm also a lazy programmer. Let's look up opt-not. Let's steal from that. I don't know. Let's just do like one. Seems fine, right? Mark, I'm sorry about your upstairs light. Okay. Johnny Lee's asking, if you make it not do the method call, would it optimize? We would have to implement the optimizations ourselves. But I mean, let's give that a try. Let's implement it as a method call first, and then maybe we can give it a try to add an optimization. So I mean, we can do that. I'll show another example of it, but let's get this test written first. Let's just do this. Expected equals is equal. No. So I'm just going to call the method and then get the value from it. Then we'll JIT compile. We'll compile the method and then compare the result of the compiled and executed method with just normally calling it. Can y'all hear the cat snoring? She's like right here snoring. Find it quite amusing. Oh, and now there's I don't know, something else. Is equal, opt-EQ is equal, okay. So compile one, execute one, enable it is equal, run it. Nah, just do expected. So is the expected value equal to what, like the called? And we expected that we compiled a method, we executed one method, and we have 0 exits. So let's give it a whirl. Test instructions. Let me clear the screen so I can get this at the top. Here, Ruby. No. What did we do? We did opt-EQ test. We'll run it. Okay, we can see here that we expected 0, actual 1 on line 20. Oh boy, can't see that. Sorry, y'all. There you go. On line 25. Oh, all right. So if we go look at that, so we exited once, and that's because we called it. We haven't implemented this thing. So let's implement it now. We'll do handle opt and handle opt-EQ, and we're just going to do the same thing. We'll treat it as a method call. Do the method call, and if we do that, what happens? All right, cool. And I ran it with so the test passed, and I ran it with debugging enabled. And if you run with -D, so let's pull this up to the top. No, that's not what I wanted. Clear. If I run it with -D here, that enables debugging mode, and the JIT compiler will output what instructions it compiled, and it'll also output what instructions it executed. So if we run this, you can see here we compiled put object, opt equals leave, and then when we ran them, this is also what it ran. And right here, this is the address of the iseq, the instruction sequence it compiled. And this SP here, this is our stack depth. So we can see like before we executed this put object, our stack depth was 0. And then when we execute it, and then when we get to this one, our stack depth is 1, and then 2, and then at leave, it's back down to 1 again. Okay, so we did that. And was asking Johnny Lee was asking like if we don't, what is it? If you make it not do the method call, would it optimize? It's not gonna optimize, but what we can do is like, let's take a look at one example of like, I don't know, less than or equal to. So we have these up here, these other optimization methods or optimized methods like opt greater than equal to, less than or equal to, whatever. And we've got this like helper function here that's compare fixed num. And what it's doing is it looks at our virtual stack. And oh, we have this guard here. So guard to fixed num. So it's looking at the virtual stack and it's like, oh, do we have 2 fixed nums on the virtual stack? So, and let me show what that means. Like two fixed nums on the virtual stack. I'm afraid that might be confusing for some people. So let's go up here and say like, okay, we got this handle opt equal. Let's go back to our test, opt eq test. So we have this function is the one that we're compiling, right? This 1 equals 1. Actually, let's change it to like 3 equals 3. 2 integer literals being compared. Now, when the JIT compiler executes, it looks at any pushes and pops. So if we're doing like a put object, and it knows what the types are, if it's able to detect what that type is, it will store it inside of the virtual stack. So like right here, when we do this compilation, let's run it again. When we do this compilation, this put object, it takes a look at whatever was pushed onto the stack or might be pushed onto the stack. So put object is special because it pushes literals onto the stack. And it tries to keep track of those types. And if we know that it's an integer, then we can emit specialized code for it. So for example, like let's take a look. We got is equal, back over in here. So let's print out the stack. We'll do like p temp stack. Let's just do p temp stack. And I'm just gonna make it exit so that we can see the output. See what it looks like. Just run it, and it didn't exit because why? Because I modified the wrong thing. We want to do the right thing. Let's see. So we'll run it, and we see here is our temporary stack. Let me go up a little bit. There we go. So here's our temporary stack. We just printed it. I should really make like a pretty print. And we can see here the item name, it's a literal, and the type is this number 21. But I have some helpers in here, so we can see like, if we do like ptempstack.peak 0, let's try peak 0 and then peak 1. So we know that the stack depth is 2 here because we're adding together the top 2 things. It should be 2, at least 2. So if we run this, let's peek at those. So it's a little less, I mean, not as gross, but here we can see, okay, so our item name is a literal and the type is 21. And that 21 actually maps to, can I open this in IRB actually? Is there like a thing I can do? It's like IRB. Is there a thing? I don't have bybug on here. Let's do PT fix num. This is that magic value, the number 21. Let's do t fix num. If we run this, okay, so we can see here like t fix num is 21 and our type is 21. So we can say like, I keep doing that fg. So we can say like, if fix num and fix num, like do something special. Let's try that. And we can see here printed out, OMG, both are ints right there. So it knows by examining the values that we pushed and popped off of the virtual stack that, hey, those are two integer literals, so we can probably do something nice here. And I mean, we could do like, it depends on like how cheating you want to be, but we could just be like, okay, let's just compare them here and return true. So like, I mean, why not? Let's do it. We'll just do like, so if both of them are fixed nums, oh, we could be like, if they're both fixed nums and literals, we'll just do the comparison and then return the value. So we'll say like, actually, do I have the number? Oh, I don't have the number. Okay. What we got to do is def. Okay, so I want to show this thing. Do def handle put object. So put object is the literal type. So when we do a put object, that's like pushing a literal onto the stack. So we can see like, let me give an example. Let's do, I don't know, 1. No, not 1. Let's do 3. We'll do 3. So we have this method 3. If we do like Ruby, you can see we got a put object here, and it's got a parameter of 3. So we're able to access that object in the instruction sequences themselves. So when the compiler goes through and processes each instruction, it's able to see, oh, there's a 3 there. Can do something with that. And the same thing with like, actually this won't work. Let's do that. So if we look at this one, we can see we got another put object here with our actual value, LOLOL, right there. Interestingly, if we delete that, you'll see it's no longer a put object. It is a put string, right? Okay. Anyway, it would be kind of interesting. There we go. Let's put handle put object. It'd be kind of interesting if here, like right here, we're only pushing the type. So we get the literal, we just say, hey, it's a literal. It's like pushing literal. And we have the object type, but we're not recording the actual object itself in the temporary stack. So when we print out the temporary stack, we just see like, oh, it was a literal, and we know that it was a t-fix num. But if we know that both sides are a t-fix num and what their values are, then at compile time, we could actually do the comparison. Hopefully that makes sense. I mean, let's try it. Let's try it. We're messing around today on my cool stuff live stream, just for fun. So let's do that. Let's do this. We can do like DL unwrap literal. So this is the value we saw. Pushed value DL unwrap. If we do that, and we run, can we run that? Yeah, yep. So if we run the test again, run this, man, I wish there weren't all these warnings, but we can see, oh, the push to value is 3. Because if you remember, our test was like 3 double equals 3. So do push value 3, and we could say like, I don't know, let's add a number, another thing here, value. Well, let's do that. And let's go into, I'm gonna change the runtime thing. Tag push. Let's do 2, and we're gonna have a value. What should our value? What should our unknown value be? Like, I don't know, because you could literally push anything. What's something that we couldn't push? I guess just an object would be like, probably that. I hope. See this, so one thing that scares me though is like, when the compiler compiles itself, actually, that's the main issue with the automatic compiler. Mediocre value, thank you. Yes. The automatic compiler, so if we enable automatic compilation, the JIT compiler will go, like, we'll try to compile some method, and then the JIT compiler will just attempt to compile itself is the issue. And we'll run into an infinite loop, which I've been working on fixing these infinite loops. It's kind of wild. Okay, null there, and we'll push temp stack to push value, and then we need to go look at the temp stack. We're gonna add a value. So the temp stack is essentially just a list of item objects, and we'll do like value, name type, value. I don't know. I'm just gonna do nil for now because we're just messing around. I'm not gonna commit this. So we'll do that, push item. All right, so now we have the actual values in here, so we can be like let's go back to the test, bu test, dq test. So we have this 3 equals 3, and can use magic comments to skip jitting certain code and then use that in the JIT compiler. Yeah, I think it's a good idea. Good, like, possibly, yes. Actually, one thing I was thinking of is, this is kind of funny. If we do, not to get sidetracked here, but it's my cool stuff. It's my cool stuff stream. I do whatever I want to. I go in here. In the set global, I made a special global that's like halt at runtime. So if you have a global that's like halt at runtime equals true, the JIT compiler will actually insert a break into the machine code it generates. So we can, like, if we're trying to debug the JIT compiler, you can be like def hard method. So let's say we're trying to compile hard method, and it's like blah blah blah. I don't know how to do this stuff, and then we can be like halt at runtime equals true, and then the JIT compiler will halt, like, when you execute the machine code that's generated for this method, it'll actually halt on this line, which is a pretty nice, like, debugging feature. But yeah, we could do something like that to be like, oh hey, I'd have the JIT compiler just skip the thing for now. I think in my branch, I basically just have a hard-coded list that's like, or maybe a regex that's like, oh, if the file name ends in like, has like TenderJIT in it, don't do that one. All right. Anyway, back over in the thing we were messing with. Let's look, test, optq test. Right. So we added the 3 to the temporary stack. So in the instruction sequence compiler, if we go look at def, what was it? Opt handle opt EQ, which is a thing we're doing. Now if we do like p temp stack dot peak 0, let's do 0 and 1. We run this. We can see right here we got the value 3. So we were able to extract those values, and we can say like, oh, okay, if they're both fixed nums, we also need to do like if. It's kind of annoying. We have to be like if name. This isn't a good name. Is that right? I need to think of a better name for this, because right now it's like name literal. It's not a name. It's not a name. It's like what it is. It's a literal. So need to think of a better name for name. Call it thing. All right. If name is literal and name. Okay. So we know here, in this case, if we enter into this thing, it's like, oh yeah, those are two literals, and we can just do the comparison here. So let's do it. We'll be like, equals what was it? What do we name it? Value. Let's just do like, I don't know, left, right. Is that right? No, it's going to be push. The left one's going to get pushed first. So this is actually right. So then we can be like, okay, so now we know the value, whether or not they're equal, and we can just be like, okay, let's do, what is it? At temp stack dot push. I don't know. True, some value thing. We need to think of a thing. Like that's a name. I don't know what to call this, but this is going to be our, let's do Boolean. Boolean seems good. And then we could be like, okay, with runtime do RT. RT dot write loc fiddle dot wrap v. All right. So this, oh, we need, we need to do though before we do this. Temp. I'm gonna pop. Make sure to pop those values. We're just peeking. When you do a pop, like the pop will just return the location. Identifier. Yeah, I like that name. Chris suggests identifier. That seems like a good, like a better name than name. Please open a pull request to rename that. Let's see. So if we do this, so when you do pop, it just returns the location where to read the variable. It doesn't return any other information about it. So like, I think that's what it does. Let's do p. I think. Oh. Mismatched indentation. What did I do wrong? I see compiler 2164. Oh yeah, that's definitely mismatched. There we go. Okay. Oh no, it actually pops the real value. No. That's an M64. Yeah, that's just a location where to read it. So we don't know anything. Like the return value of pop doesn't really tell us anything about the value that's on the stack, except the location in memory where to read it. So anywho, maybe we want a different thing that's similar to pop, but returns like the actual item object so that we can get access to these things. Because right now we just have to peek at it and get the values. Anyway, Let's try running the test again. I think this will work. It did not work. Why? Wrap is wrong. It is. I keep doing that. DL wrap. Oh man, that totally worked. Awesome. Pop deref. Yeah, I like pop deref. So now in this case, we're able to say like we optimized for the case where there's two integers, and we're just doing a comparison, and we're able to actually cache inside of the inside of the machine code itself the the resulting value of the equals, because we just like right here we're doing the comparison at compile time. So we'll do like compile time comparison. Now you may be asking yourself, what if I'm a really cool programmer and I was like numeric def equals, I would say please don't do that. But yeah, this will not handle, it won't handle monkey patches. TenderJIT doesn't handle monkey patches right now, which is another like thing on the to-do list, but we'll be able to do it. Like we should be able to do it. So I mean, maybe this isn't too bad. Like we could probably keep this, because essentially what you could do is be like, okay, if somebody does the monkey patch, then we'll like throw away this JIT code and recompile it. So we could get away with doing this comparison at compile time. Actually, let's commit this, I guess. Oh, let's make a branch. Let's make a branch that's like, I don't know, live stream. What is today? 18th, 19th? All right. What do we do here? We did this. Oh, we don't want that. I definitely don't want that. Let's just do... No. Let's do like bumping up size requirements. All right. So I think we can make this configurable, because if we look at so if we look back here, so the size, I think, yeah, the size is actually, this size constant is actually used inside of the TenderJIT initialize function. So we could just be like, we could pass it in. I mean, you could really just do that, fix all these to be size. But I just haven't, because I'm lazy. Johnny Lee Rollins asks, is it possible to use the shape of the Ruby object to detect whether it's complex or comes from a list of known types to optimize? So, yes, kind of. Like, Ruby doesn't have object shapes in, I guess, the, I don't know, traditional compiler sense necessarily, but we have, well, traditional compiler sense, I don't know what the fuck I'm talking about. Oh, I don't know what I'm talking about. We don't have object shapes per se, but we do have like a type tag on the object, so we can figure out what type it is. So we can say like, is this a t fixed num, or is this a heap allocated object, or is this, you know, what is this thing? A float, whatever. And we can use that to figure out. We can use that to apply some optimizations to the object. But for example, things like where the idea of object shapes would come in would be with things like instance variables. So for example, right now we have to know, like, we don't know, when the compiler executes, we don't know how many instance variables are going to be on an object. So when we say like, hey, we got to get an instance variable, we don't know where to get that thing from, because we don't know how many instance variables there are or where they are stored on the object. And that's where That's where object shapes could really come in handy, is like tell us, oh, okay, this is an object that has 4 instance variables, so we know where to access each one of them. But yeah, that is definitely a thing. But we can kind of do it now, but it's pretty limited. Like this, I see compiler. I mean, that's essentially what we're doing here when we say like fix num. So this fix num is like when we do the push, we're checking what is the type. So if we do def handle put object. When we're doing this push here, we're checking this type. So we have this rb type method. Let's go take a look at that method. It is in right here. And essentially what we do is we're like, hey, is this a special constant? Meaning, is it a type? Like, special constant means address that doesn't have any of the bottom 3 bits set. If it is a special constant, then when we check, oh, is it q false? Is it q true? Is it nil? Then we check if it's none of those. Then we check, oh, is it a fixed num, static symbol, etc. Otherwise, we grab whatever the type is. The type is from the heap allocated object. Like down here, this is allocated from the GC, so we can know that type, and based on those types, we can do some optimizations, but they are pretty limited. So, like this one that you saw here is like kind of the extent of it, basically, right now. Okay, what else should we do? Let's commit this. We really don't want to check this in. No, let's not do that. I like this comment. I'm not going to discard it. Let's add the test. Get the test here. Okay, that's good. I don't want to add the specialization right now. I just want to do like, I like the specialization. I think it's fun. And maybe I'll do it, but I want to do something better. So it'd be cool if we could handle more than just like fixed nums. And we also need to figure out like, oh, what to do about monkey patches. The nice thing about just doing the method call is that we stay inside of the JIT. As I was talking about earlier, exiting the JIT is kind of catastrophic. So we stay inside the JIT. Yeah, you know what? I should just commit it. No, we're not going to do it. No. Not going to do it. Because we had to modify the temporary stack too, but I do like I like the change. It seems like fun, you know? All right. We'll add that. Nope. We'll no, I don't want to stash that. I do want to stash that. Yeah, sure. Whatever. Wait, no! Oh my god. Someone tell me what commands to write. Did it work? Is it in here? Is it still here? Oh, it's still here, even though I said yes on stash. Okay, whatever. Okay, we're gonna do sporting is what is it? Opt EQ. Yay. Okay. Now what? Oh, okay. Get status. So I think we're good now, except for you can see my mess in here. This is my normal development environment, is leaving a mess on the main thing. Oh, what's this? What? I don't want to do that. I don't know how that happened. Okay, I think we're good now. Let's do rate test. All right, cool. So we got all those running. Let's see. Let's check what's next on the list, like out of OptCarrot, and then I think I got a meeting in 5, so I think let's just check OptCarrot, see what's going on there, and then stop, so we can figure out what our next target is. OptCarrot. Let's do that. Okay. OptCarrot. All right. So still 7 methods, still 181 exits. So it looks like probably our code somewhere has like a not and then an expand array. And expand array is, so we're not gonna do expand array today. I think expand array is this thing I was messing with earlier in my little test program. So like this here, x comma y equals a. I think this is our test case. So if we run this, let's print out the instructions from that. So we're saying set local a dupe array. So first off, we have an array which is let's cat test our RB. Okay, so we have can we see? Yes. Okay, I'm not in the way. Good. So we have an A that's an array literal. So we dupe an array, we set the local, then we get the local right here. We're getting the local, and then we do expand array 2, 0, and that assigns out our X and Y. So I don't know if I'll do, I mean, maybe I'll save this one for the next live stream. Maybe I'll just do it. I don't know. But anyway, I think let's end here. Happy Friday, everybody. Thank you for coming. It was good to type some codes on the live stream. And I will see you next time. Bye.